So we're going to talk about nuclear power. Controlled and uncontrolled. When you control it, you can make electricity for towns and cities and counties. When you don't control it and you just let it proceed on an uncontrollable runaway scale, you get weapons. So the first thing I would like to talk about is nuclear fission. And fission is the opposite of fusion. So fission means to separate. This is what's used in nuclear power plants, like where Homer Simpson works, and it's also used in nuclear bombs. This past summer, the movie Oppenheimer came out. J. Robert Oppenheimer was the lead scientist in the Manhattan Project in 1945, which was about creating a weapon so massive that you would be foolish to want to fight against it. And they knew the Nazis were also trying to create something like this, but they hit a wall. They were stuck. J. Robert Oppenheimer was an American scientist, and he and his team created the first bomb that they used in New Mexico. It was at the Los Alamos test site. That was in July 1945. So they immediately told Japan, surrender now or face obliteration. And Japan says no. And so they dropped the bomb on Hiroshima, August 6, 1945. Totaled the town. They said, do you give up? Japan says no. So 3 days later, August 9th, 1945, Nagasaki. And eventually, Japan's general said he didn't want to quit, but the emperor said, we're quitting. We can't take this all day. Here's something you guys may not have learned in history. We only had 2 bombs. We just had 2. But Japan didn't know that. And so we were hoping they wouldn't call our bluff. We can do this all day. We'll just blow the whole island chain out. Do you want to keep going? After the second one, when we bombed Nagasaki, they surrendered. If they didn't surrender, who knows how long the war would have lasted, because we only had 2 bombs made, one for Hiroshima, one for Nagasaki. That was it. So it's like we were daring them to call our bluff, and they didn't. So we won. And those are the only 2 times that atomic bombs have actually ever been used in warfare. There's been so many tests. If we have time tomorrow, I'll show you a video of all the tests that have been done. It's more than 2,000 bombs have been exploded due to testing, but only 2 have been used in warfare. August 6th, 45, and August 9th, 45, when the USA bombed Japan. So nuclear fission is how those bombs were made, and it's how we also make nuclear power. So as you all likely, hopefully know, heavy nuclei tend to be blank. You tell me, do heavy, big nuclei tend to be stable or unstable? They tend to be unstable. So what do heavy nuclei that are unstable tend to go through in order to achieve stability? They go through decay. Good. So to gain or achieve stability, they fragment into smaller nuclei. This is known as nuclear fission. Taking something big, splitting it up. You got to remember this. Fission means to split or to separate. You're separating them. Now, not only does fission result in the separation of one nucleus into 2 nuclei, it releases a tremendous amount of energy. I'll get it. Fission is accompanied by a very large release of energy. If you get enough fuel to go through fission, you can have quite a big bang. It just depends on how much you have. And if you can control it, or if you just want to let it proceed out of control, like on a bomb. So what I would like to speak about first are nuclear power plants. There's a lot of conversation in this country about switching from coal power plants to nuclear power plants. Coal produces carbon dioxide, which pollutes the environment and can drive climate change. Nuclear power plants don't have that. They're a lot cleaner, but there is a side effect, and I'm going to teach you what that is. Unlike coal-powered power plants, nuclear power plants, like where Homer Simpson works, use fission to generate electricity. And it's a lot cleaner when it comes to like pollution. When you guys go out to Bayshore Boulevard, and if you look across Hillsborough Bay towards Riverview, you'll likely see the TECO power plant. It's been there since way before you were born. They call it the Big Bend power plant because Big Bend Road is over in Riverview and it's at the end of Big Bend Road. It releases a lot of exhaust from burning coal to creating electricity. That's actually keeping these lights on and this computer on right now. We're in Hillsborough County. TECO is our power provider. Your parents pay a monthly bill to TECO for all the electricity used in your house. Well, in nuclear power plants, they use uranium-235. The majority of uranium is 238, and it cannot go through fission. But an isotope of uranium is uranium-235, and it can undergo fission. It can be split. And so in nuclear power plants, you want to use this. But you got to split it. Here's the catch. You got to have something to split uranium-235. And so in the movie or the videos that you all are going to watch in a few days, they use neutrons. And neutrons are going to be referred to as a bullet. If you fire a neutron at a uranium-235 nucleus, the nucleus will split. But it can't split without that neutron. Neutrons are fired at uranium-235 nuclei to trigger fission. And rather than draw this, I want you to get a good look at it. I was going to have you draw it, but I think it would take too much time, so I found an image. And you can look at this image on this YouTube video if you like. I don't want you to draw it. You'll be here for the next 10 minutes trying to draw this, so don't do it. I'm going to grab this image and bring it over here. This image is a representation of fission, okay? So take a look. This is uranium-235. It is unstable, but we have learned to control its decay. So what we do in a nuclear power plant is we take a simple neutron, like what you find in the nucleus of any atom, and you fire it at uranium. It will then cause uranium to split or go through fission, fizz. And it's going to split into barium and krypton. But not only does it split into barium and krypton, look what else comes off. 1 neutron, 2 neutrons, 3 neutrons. Now, Aiden, to show me that you're following this, When uranium is split, it splits into two new elements, and it also produces 3 neutrons. Where does it look like those neutrons are heading? To split what? Split more uranium, okay? So, Aiden, based on this uranium nucleus right there, how many neutrons were formed from that? That's right. Now, so how many neutrons can be formed from each uranium that is split? Good. So I have 3 uranium atoms being split. How many total neutrons will that form? 9. Now look up here. Whoops. Let's go here. Shoot. It's not working how I wanted it. There we go. Let's look here. You're now splitting that. Here's 1, 2, 3. 1, 2, 3. 1, 2, 3. All right, Aiden, put on your mental math hat. How many total uranium atoms do you see here? How many neutrons would be released from each of those uraniums? So what's 3 times 9? 27. And then if you did that times 3, you get, that answer. It just keeps going and going and going. But the last thing I want you all to see here is this: energy released, energy released, energy released, energy released. This is what atomic energy is all about. When you split the nucleus, it releases a tremendous amount of energy. And that's what we use for power or we use for destruction, whether you're talking about nuclear power plants or atomic bombs. This is called a nuclear chain reaction. And I hope you can see why it's a chain reaction. One neutron breaks apart one nucleus of a uranium, and that results in 3 neutrons. You then have 3 uranium nuclei just sitting there. They get hit with a quote unquote bullet, and then they split. And now you have 1, 2, 3, 4, 5, 6, 7, 8, 9 neutrons. They hit another uranium, and it just goes more and more and more and more. And every time a nucleus splits, it releases a tremendous amount of energy. This is called a nuclear chain reaction. You will hear about this a lot when we watch Chernobyl. Neutrons are fired at uranium 235. This leads to fission. This results in 1, barium 151, 2, krypton 92, and 3 neutrons. It's these neutrons I want you to focus on. That's the important part. These neutrons are really important. The neutrons collide with more uranium 235, triggering more fission events. With every fission event, more energy is released. And as I've said a few times already today, we can either control this and slow it down and make electricity for your house, or we can just let it go crazy and make an uncontrollable release of energy, which can lead to an explosion, which we've used in weapons. There's not a lot of countries in this world that actually have nukes. Russia, China, America, France, England, India, Pakistan, they have them. We're pretty sure North Korea, who's not nice to us, has it. We're pretty sure that Iran, who's not nice to us, is on the cusp of getting it. I think that's all the nuclear powers. Not a lot of people have them. Okay. So this nuclear chain reaction can be controlled, which is what we do in nuclear power plants. Or uncontrolled, where you just let the reaction go off the rails, and that can be used in a bomb. Nuclear bombs are not designed to explode on impact. They're timed. They're timed so you can let two pieces of uranium crash into each other. There's a little trigger inside, and the timer sets off the trigger. They do not explode on impact. Okay, so I want to switch over to Google Maps here because there's actually nuclear. I want to show you how close the closest nuclear power plant is to us. So let's go over here. All right, so here's Tampa Bay. I'll zoom in on Plant High School. Where are you? Here it is. There's us. South Hall is right there. You guys are in that building. Zoom out a little bit. Go to Bayshore, right there. You go across Hillsborough Bay. And right here, where is it? Let's go down a little bit. Yeah, here we go. This is the Tico Big Bend Station. This is the big power plant that you see when you're out on Bayshore. You look across the water. That's it. That is a coal burning power plant. They also are trying to transition to a lot of solar, which is cleaner. But this does not make as much electricity as what I'm about to show you. If you go about 70 miles north of here, let's go along the Gulf Coast. There's Pinellas County. Let's go north a little bit. Zoom out a little. All right, there it is. This is the Crystal River nuclear power plant. It's about 70 miles north of here. There's those big cooling towers that you've likely seen on The Simpsons where Homer works. That stuff coming out of there is not smoke, it is steam. I'm going to tell you what in the world steam has to do with a nuclear power plant. But most power plants like this are located near the water because you need water to cool down the nuclear reaction so that it can be controlled. But that's the closest nuclear power plant to us. It's within 100 miles of here. Okay. So let's see what I want to do next. Let's talk about a nuclear reactor. A nuclear reactor generates electricity. This is the main place inside of a nuclear power plant where the actual nuclear fission is occurring. Yes, Varun. What would happen in Tampa if that power plant? Depends on which way the wind is blowing. There won't be an explosion that can cover that much mileage. We would likely hear it. We might even get a shock wave from it. But if it were to explode, it would be up there, but depending on which way the wind is blowing would determine which way the radiation would go. All right. The fuel source for a nuclear reactor is uranium rods. You're going to hear a lot about the uranium rods when we watch Chernobyl. Remember, this is uranium-235. These rods they're going through fission. They're rods that actually had uranium-235. They can go through fission. But here's the thing, guys, and this is what I want to make clear to you. If these rods are going through fission, then they are releasing neutrons. The neutrons are firing out of the rods. We want to control that. We want to slow it down, and we want to control it so that we don't have a big explosion every time we're trying to make electricity. So the fuel rods emit neutrons. So I want to make that clear. But we want to control it. So there are also rods made of cadmium and boron. That control the fission process by absorbing those neutrons. So you do not want this chain reaction I showed you to just go out of control. And if it did, I mean, nuclear power would not be a thing because we got to be able to maintain it. And so whenever these rods are going through fission and releasing neutrons, you want to absorb those neutrons so you don't just have a runaway chain reaction. This is why people like Homer Simpson have a job. Nuclear technicians must be present all the time and to control these and observe these processes when they occur. Nuclear technicians must control and monitor the chain reactions to prevent them from racing out of control. That would be bad. And that's actually what happened in Chernobyl. You'll see exactly what happened. Chernobyl was in 1986. It was the worst nuclear disaster in this planet's history. There were two others I'm going to show you today, which were not as bad. And so what I would like to do here, take a little break from writing. So I want to show you how a nuclear reactor actually works. And it's actually pretty easy. It's not complicated. When you hear about thermonuclear physics, right, that sounds pretty tough. It's honestly not hard to understand. So I'll break it down for you. Just drag this image down here. Now, I cannot help you understand it if you don't pay attention. So that's on you. So here we go. What you see here is a nuclear reactor. I'm going to turn lights off so you all can see it better. We call this the core, where the actual nuclear reactions are happening. It is very, very hot. Radiation emits a tremendous amount of heat. It will melt you and turn your insides into goo in no time. So this is the reactor core. And inside the core, you have these fuel rods and you have control rods. The fuel rods are made out of uranium. The control rods are made out of cadmium and boron, and they absorb neutrons that are released during fission. So what you have to do is you have to keep it cool. These reactor cores are some of the hottest places on the planet. They're very hot. I think it's more than 200 degrees, no, 2000 degrees Celsius. I can't remember exactly what it is, but it's really hot. So what you do is these rods are generating a lot of heat. Now, what happens to water when it is superheated like this? You form steam, okay? This steam is going to be funneled through this tube into a turbine. A turbine spins very fast. And one thing that's very easy about physics is the faster things move, the hotter things get. So this turbine is spinning really fast from all the steam. This turbine generates electricity. And that electricity goes out to homes and towns and cities to keep the lights on. So the real thing that's powering a nuclear power plant is hot water. How do you make the water hot? You have nuclear fission happening. You make the water so hot and the steam so hot, it's hot enough to spin this turbine. And this turbine generates electricity, which goes out into the power lines and it keeps the lights on. But what happens to all that steam? Well, what happens to steam when you cool it down enough? What does it turn back into? Liquid water. This liquid water is going to go into the water pump. And it's going to get cycled back into the core. And so the water is just cycled over and over and over. But also, the warm water is going to be sent to these cooling towers. And that's what you actually see coming out of those big round stacks that are at nuclear power plants. It's not smoke. It's just steam. It's steam from this process of keeping the core cooled down. So let me ask you this. What would happen if you had a nuclear core with no water to try to keep the reaction cooled down? What do you guess, Alex?
It would explode. Or it would go uncontrolled.
Why would it explode?
There's nothing to stop the reaction, it just keeps going.
The reaction is happening faster because it's out of the water. Now, what do you think would happen to the uranium rods when they're out of water? Are they going to get hotter or are they going to get cooler? This is called a meltdown. When you hear of a nuclear meltdown, it's when these rods, these uranium rods, are no longer in the core. That means that they're no longer in water. They're out of the water. And they're so hot, they actually melt. And when you hear meltdown, the whole reactor can actually melt into the earth. And if the uranium rods are exposed out of the water for too long, they can trigger an explosion from all the gases that are starting to form through the nuclear reactions. You're going to have, here's the thing, and you'll see all this in Chernobyl. The water slows it down. It slows the reaction down so that humans can control it. The technicians in the front offices, they control it. But if you have the uranium rods out of the core, fission is happening still, but it's happening faster. And it's producing barium. It's producing krypton, gases. Krypton, something y'all don't know yet, and you'll learn this in Unit 5. Krypton is a gas. Everything in this column on the periodic table is called the noble gases. Everything on this periodic table that is red is a gas. And so krypton, amongst other stuff, is being produced. And when you have all this gas building up and building up and building up inside the core, it's got to be released somehow, doesn't it? What happens to a balloon when it gets filled up with too much air? Well, yeah. The uranium core or the nuclear core basically pops because it's filled up with so much gas from the fission reactions. And the top blows off, and that's what happened in Chernobyl. The rods were out of the core. That means krypton and other gases are just filling up the core, and the core can't contain the gases anymore, and so it blows up like a big balloon, but a nuclear balloon, and it just explodes. Okay. So continuing with this, with a nuclear reactor. Reactors are built inside of thick, and I really want to emphasize that, thick concrete walls to contain harmful radiation. And here's something that you'll learn about when you see Chernobyl. Here in the United States of America, we actually invest a lot of money into the nuclear power plants to make them safe. Back in the 70s and the 80s in the old USSR, which is now Russia, they skipped out on making things safer because it was cheaper. And that was one of the downfalls of Chernobyl and other nuclear power plants in that part of the world, is they built them differently there. They built them cheaper. And the concrete wasn't as thick as it should be, because all this concrete is meant to contain the radiation. Now, I told you that nuclear power is cleaner, but then I followed up with a but. And my dad would say everything you say before the word but is crap. It's like saying, Alex, you're a really nice kid, but. So, okay, I feel a but coming on. It means everything you just said before really doesn't matter, does it? Nuclear power plants do not really release any pollution. They do not contribute to climate change. They don't have any CO2 going in the atmosphere. They have a different form of waste. Spent fuel rods are considered nuclear waste and must be replaced. Some of the rods can actually be reused, but when it comes to rods that can't be used anymore, here's what you do. You bury them, or I think this is on your test. There's a place, I think it's in New Mexico. It's somewhere out west. New Mexico, let me see. Hey Siri, where is the Yucca Mountain?
Here it is on the map.
She's not showing anything. Hold on. Let's try again. Hey Siri, where is the Yucca Mountain? It's in Arizona. The Yucca Mountain is basically a United States of America's dump for nuclear waste. It's where we store all the nuclear waste, nuclear like rods, just nuclear, just trash, all the stuff that we can't use because, guys, the stuff is radioactive for at least 40,000 years. That's a long time. So you just got to keep it away from everybody. So they bury you deep within a mountain so that no one will be exposed to it. So the waste remains radioactive for thousands of years. If you went to Chernobyl today and we watched the video when we started this unit, it wouldn't be pretty. The basement in Pripyat, which is the city closest to the nuclear power plant, still has, as I'm talking to you right now, it still has the boots, the jackets, and the pants from the firefighters who responded to the explosion that night. Because when they were standing at the base of the power plant, they got radiation all over them. And the radiation got in their clothes. And the nurses realized this. So they took off, they stripped the firefighters down to their underwear, and they carried all their boots and jackets and helmets and everything to the basement. And I'm serious, if you went to Chernobyl today, as I'm talking, you went down to the basement, you had a Geiger counter, which I'll teach you about tomorrow, a tool that can measure radiation, it would be one of the most radioactive places on the face of the earth. Their clothes are still there. No one goes back there. Chernobyl to this day is pretty much abandoned. Yes. Yeah. He was wearing a full radiation suit, and he knew he couldn't be there for very long, even with that material. All right, got you for a couple more minutes. Let's do what do you think the opposite of fusion? What's the opposite of fission? Fusion. Let's talk about nuclear fusion. Fission is splitting. So fusion is uniting. When you have fission, you have one large nuclei result in two or more smaller nuclei. Well, in fusion, you have two or more smaller nuclei result in one larger nuclei. There is far more energy produced in fusion as opposed to fission. But here's the problem. We haven't really mastered it yet. You guys need to remember where, in our current level of technology, we have our limits, but our limits are being knocked down all the time. The only place in nature that fusion really happens is a star. You have hydrogen 1 fuses with hydrogen 3 to form helium. Or no, hydrogen 2, sorry. Forms helium and a neutron. The sun is the only place where you actually have fusion happen, and it can be controlled because it's so hot and the gravity is so strong, it forces nuclei together. We have not mastered this yet. We're trying to, but here's the problem. It's a little tough to try to create a sun on the Earth. Now, I'm not talking about a sun like a baby boy. I'm talking about a friggin' star. It's a little tough to try to create one on planet Earth. So we're trying not to blow up the atmosphere while we do it. It's a science that we haven't exactly mastered, but what we do know is that the energy that fusion creates makes fission look like a firecracker, like nothing. You could probably power this entire continent for 1,000 years if we could figure out fusion. All right, tomorrow I'm going to finish it up with some bombs.